Welcome to linear integrated circuits videos. So in this we are looking at triple five timer applications. Now this is a video in which we are seeing the advanced portion compared to the basic where we learned the working of the monoshot. So we know monostable multiverter has got one stable state and another state is quasi-stable state. So quasi, we know that it's a temporary state. So in monoshot, output will remain in stable state of 0 volt unless circuit is triggered to go to quasi-stable state. So upon applying a trigger signal of voltage less than 1/3 VCC, which is VTL, the monoshot goes to quasi-stable state of VCC for a predefined time of t seconds, and then it comes back by itself to a stable state of 0 volt. So this is how a monoshot can be forced to go to quasi-stable state. Otherwise, it remains in the stable state. Okay, we know that in the previous videos we have seen the circuit diagram for the monoshot multioperator. The corresponding waveforms of this monostable multioperator with the trigger signal going below VTL. So we know that when the trigger signal goes below VTL, the capacitor starts charging towards VCC. Once it crosses VTH, the output will become 0. So meaning when the capacitor is charging from 0 to VTH, the output goes to quasi-stable state of VCC, and as the capacitor voltage crosses VTH, the quasi-stable state ends and then the output goes to stable state of 0. So this is the general working of monostable multioperator. Okay, this monostable multioperator will remain in stable state of 1, so till a time of t, which is defined by these external components R and C, that is 1.1 into C into R. So let us consider a few examples when trigger signals are in different conditions. Let us consider a trigger signal which is VCC over here, and it is like a pulse, but it is never going below VTL, that is 1/3 of VCC. So this is 1/3 of VCC. If it is not going below 1/3 of VCC, let us see what happens to the output voltage. Now we know that in the previous videos, so in the detailed, suppose if the voltage here is not going below VTL, this comparator will never become 1. So when this comparator is not becoming 1, the output will remain the previous state of 0, meaning the output will never go to quasi-stable state, meaning the output voltage is always 0 because the trigger signal is not at all going below VTL. So it is always necessary that we should not only see the shape of the signal, we should also see whether the voltage is going below VTL or not. Unless it doesn't go below VTL, the output remains there in stable state. Let us consider a second example where we are intended to have a monoshot multivibrator with R is equal to 1 kilo ohm and C is equal to 1 microfarad, which results in a pulse width of 1.1 millisecond. We have applied a trigger signal which is VCC and then going to 0 volt, but you can see here, so this is in 0 volt for 5 millisecond, and here we want to have a pulse width of 1.1 millisecond. We can certainly see that this trigger signal is certainly going below VTL, and it stays there in that state of 0 volt for 5 millisecond. Now let us see how does the output looks like. Now see here, the capacitor voltage will start charging towards VCC. I can see it is going towards VCC here, and it has gone here. Now it has crossed VTH. It has crossed VTH, so it is still charging here because capacitor is allowed to charge even beyond VTH because the output, the input trigger signal is still 0. So this, when the input trigger signal is still 0, the output will be always in set condition. Once it's in set condition, we know that transistor will be uh, sorry when the output is in set condition, the transistor is off. So when the transistor is off, the capacitor is keep on charging there. So since it is keep on charging, this capacitor was supposed to come down here. Now it is still charging towards VCC. Now let us see what the corresponding output is. This is the corresponding output. As you can see now, so your trigger signal went below VTL. The output has increased to VCC, went to quasi-stable state. So when it went to quasi-stable state, we expected this to come down to this quasi-stable state was supposed to end at 1.1 millisecond as per this condition, but it is still extended beyond 1.1 millisecond. It is only because this trigger signal is not removed at 1.1 millisecond. So it is always necessary that this trigger signal which is going below VTL should be there for a very small period, and this period of 1.1 millisecond should be taken care by RC. Now in this case, what is happening? The trigger signal is extended till 5 millisecond. So as long as trigger signal is less than VTL, till the time the output will be high. So output is not the quasi-stable state is not decided by the external components, but it is now decided by the off time, that is the zero time, the time up to which your trigger signal is less than VTL. So this is not exactly tallying with our t is equal to 1.1 millisecond. It is only because the trigger signal is 0 volt for 5 millisecond. Now let us consider one more example where R is equal to 22 kilo ohms and C is equal to 0.1 microfarad, which results in a pulse width of 2.2 millisecond. Assume that we have something like this type of signal. So at 1th millisecond, so output is going low for a very small duration, and at 2nd millisecond it is again going down. At around 4.5 millisecond it is again going down. Now so let us see, since it is going down and it is below VTL, so which is a valid trigger signal. Let us see what happens. I can see this for the first time the voltage is going, the trigger voltage is going below VTL. The output starts charging. Now you can see it is start charging. We have one more trigger signal over here, so this trigger signal will not be considered because it is already there in the quasi-stable state. The capacitors keep charging, so this will be keep charging towards VCC whenever it crosses VTH. So at that time trigger is VCC, so trigger is not affecting our output. The output, the capacitor voltage starts discharges immediately after 2.2 millisecond. Now even though we have a one more trigger signal before that pulse width, so this will not be considered. So this will be considered as a valid trigger signal. It is capacitor is charging and the output is, here you can see the output has gone to quasi stable state. It remains there in quasi stable state for 2.2 millisecond and it comes down and it sees one more trigger signal, that is voltage going below VTL. The output goes to quasi stable state, remains for 2.2 millisecond and then comes down by itself. In the previous case it was not coming down after the predefined time because the trigger signal was still 0. So as you can see here, the trigger signal is still 0 even after 1.1 millisecond, so that's why this was not coming down. So always ensure that this trigger signal should be low and then it should go high immediately so that it can charge up to VTH and then come down at 1.1 millisecond. Now let us consider one more example where we have a trigger signal which is an AC signal, that is it is going above 0 and then below 0 here. In such case, okay, we get a output waveform something like this. Here you can see in this example we have designed the mono shot with the value of R and C as 1 kilo ohm and 0.1 microfarad, which results in a pulse width of 110 microsecond. But unfortunately you can see we are getting a pulse width of 2 millisecond. So our input is going below VTL, at second millisecond, so it is there up to 4 millisecond 0, and then it is again rising. So as we saw in the first example, the as long as the trigger signal is less than VTL, the output is there at high state, irrespective of your capacitor is charged to uh, VTH or not. So you can see now it is still at high state because your trigger signal is in a voltage less than VT. Uh, this is voltage less than VTL. But here you can see the practical pulse width of this output waveform is 2 millisecond, whereas the theoretically we want to have 110 microsecond. So practical is not tallied with the theoretical one. It is purely because this time is more. So in such case, if we have such type of trigger signal, how to uh, how to get a practical pulse width equal to theoretical pulse width? Now I can see it is the same trigger signal. Now we want to generate a trigger signal of this nature to obtain a proper pulse width of 110 microsecond. So I can see now we have this is a trigger signal derived from this one. So instead of applying this square wave, which is an AC signal, we are generating spikes and then we are applying the this as the trigger signal for monoshot. If I apply this type of signal as a monoshot trigger signal, now you can see as long once the voltage goes below VTL, the outputs go to quasi stable state, remains for 110 microsecond, comes back. So this is what is valid here. So here it is going down below VTL, which is made to go down like this. But here you can see this was remaining for minus 5 volts or minus VCC for 5 millisecond. Now this waveform which is derived out of this will going to generate a spike. Now you can see it is going immediately back to VCC, so that the trigger signal is removed once it has initiated the MOSFET to sorry the 555 timer to go to quasi stable state. It remains there in quasi stable state for a predefined time of 110 microsecond. It comes down. You can see now the capacitor voltage charging up to VTH. It comes down immediately because whenever it is coming down, so the trigger signal is removed here. So this should be much more sharper here. So this should be sharp. This is above. By the time the capacitor voltage has reached VTH, the trigger signal is certainly above VTL. Now this is the circuit which is used to generate this spike signal using this square wave waveform. So I can see you have a capacitor, you have a resistor which is tied to VCC, and there is a diode which is making the positive spike limited with a amplitude of VD on. So this circuit is a differentiator circuit clamped to VCC. So it is very important that we should make sure that the trigger signal voltage less than VTL is for a very small duration, which is certainly less than the pulse width of the desired output waveform. Now let us take the same example because we are not used to this type of circuit as a differentiator. Let us see how do we evolve that differentiator circuit. Now this is the square wave. If we consider this type of differentiator circuit, we end up with uh, spikes which is generated for every changeover of the signal. So we're going to get spikes here. So you can see since the voltage is less than VTL for longer duration, we get an output voltage which is something like this. This is not again practical is not equal to theoretical, so we cannot use this differentiator circuit to generate the spike. I can see for so much of duration it is less than VTL. For that much period the output is at high state. You can see we are now clamping this to VCC. We end up with a waveform now. The previous waveform was at 0 now. This was centered at 0. Now it is centered at VCC. Now it is clamped to VCC. Now you're getting a generated signal. Now for a very small duration it goes to a state which is less than VTL, and output goes to high state. This T is exactly equal to our T theoretical is equal to T practical. So in order to just ensure that this doesn't cross